Chapter 16. This chapter is titled Solubility and Complex Ion Equilibria. Our outline is KSP and solubility, common ion effect, pH and solubility, precipitation, and qualitative analysis. KSP and solubility. Imagine we add a salt like silver chloride, AgCl solid, to water. If we add very, very little and very slowly, at first the salt dissolves. Once we reach the saturation point, all that will dissolve has dissolved. If we add more salt, there will be some solid in the bottom of the solution. The solid salt and its ions are in a dynamic equilibrium. Actually, the solid is dissolving, the ions are coming together to give solid, so it's a dynamic equilibrium, but they are in equilibrium. Our reaction would be, in that dynamic equilibrium, AgCl solid in equilibrium with Ag plus aqueous plus Cl minus aqueous. The maximum amount of AgCl that will dissolve at around room temperature is 1.3 times 10 to the minus 5 moles per liter, or in grams is 0.0018 grams per liter. These equilibrium concentrations are the highest concentrations possible before precipitation occurs. And thus, these concentrations describe the solubility of the salt. So the solubility is how much will dissolve in a certain quantity of water. Solubility is the maximum amount of salt that can dissolve per volume of solution. Solubility can be expressed in moles per liter, grams per liter, grams per ml, grams per 100 mLs, etc. The product of the equilibrium concentrations, so those are the maximum solubilities of the ions, raised to appropriate powers, which are the stoichiometric coefficients, is equal to KSP, where KSP is called the solubility product. So once again, the product of the equilibrium concentrations, and these are the maximum solubilities of the ions raised to their appropriate powers, which are the stoichiometric coefficients, is equal to what's called KSP, where K is, as before, it's an equilibrium constant. KSP is called the solubility product, SP, solubility product. KSP is equal to, in this case, Ag plus times Cl minus. So AgCl solid is a pure solid, so it's not included in KSP. So here's our reaction at the top of our page here. So if we look at that reaction and we write the equilibrium expression from it, we would see Ag to the first power times Cl to the Cl minus to the first power because of the 1 stoichiometric coefficients. And AgCl is left off the solid because it's a pure solid. So recall way back to our chapter 13, the pure solids as our pure liquids, those are left out of our equilibrium expressions. KSP concepts apply to, we use them to apply to slightly soluble salts, ones that have such a small solubility that they're often referred to as insoluble. That would include AgCl. From solubility, we can calculate KSP. So if we're given solubility, we can calculate KSP. If we're given KSP, because those are values in tables, we can calculate solubility, so we can go back and forth. KSP values for various salts are found in KSP tables. So here is a KSP table from your textbook. So they are organized by the anions, like we have the fluorides, chlorides, bromides, so iodides and so forth. So chlorides, so there we see AgCl, we see a KSP value for it at 1.6 times 10 to the minus 10. Notice that KSP values of these almost insoluble salts are often very small. I see some that are 10 to the minus 54, so very small numbers. So next we have some calculations where we go from solubility to KSP or from KSP to solubility. We will do this problem here where we're given the solubility of silver chloride to be 1.27 times 10 to the minus 5 moles of AgCl per liter of solution. And we will calculate the KSP from that. Indeed, the table we just looked at has KSP values, but we're going to see how to go from solubility to KSP with this problem and the next one. The solubility of silver chloride, 1.27 times 10 to the minus 5 molar, is about the value we had used earlier. This is to 1 more sig fig. Alrighty, so what we do is we write out our reaction AgCl solid in equilibrium with Ag plus Cl minus. We do our ice table where the initial amounts of those two is 0 and then they grow a bit by x. At equilibrium we have x. So we have KSP equals Ag plus times Cl minus. We're representing those each by x, so KSP equals x squared, and x is that solubility. So we have 1.27 times 10 to the minus 5 squared, or we calculate a KSP of 1.61 times 10 to the minus 10. And the reason that we have 3 sig figs in KSP here, as opposed to what we saw in the table, only 2 sig figs, is just because of the solubility having 3 sig figs that we used. Our next problem is the solubility of Ag2CO3 equals 1.3 times 10 to the minus 4 moles of Ag2CO3 per liter of solution. Calculate KSP from it. So our reaction is Ag2CO3 solid in equilibrium with 2 Ag plus CO3 2 minus. We do our ice table. They each start at 0 and they change in this way. The silver changes by, you might say, 2x or 2 times the solubility, and the CO3 changes by x or just the solubility, the 1.3 times 10 to the minus 4. So at equilibrium, we have 2 times the solubility for Ag plus. We have just the solubility for CO3 2 minus. And the 2 there, of course, you recognize comes from the stoichiometric coefficient in front of Ag plus being 2. So KSP is Ag plus squared. Remember, we haven't done that in chapters 14 or 15 because everything was on a 1-to-1 mole ratio. But with our solubility chapter, well, they're not necessarily. So Ag plus squared times CO3 2 minus to the first power. So Ag plus is 2 times 1.3 times 10 to the minus 4, or 2.6 times 10 to the minus 4 squared, times 1.3 times 10 to the minus 4, and we calculate the KSP to be 8.8 times 10 to the minus 12. Now, let's look at the solubility of the AgCl, which is smaller than the solubility of Ag2CO3. The Ag2 solubility is about 10 times greater. And yet, the KSP we calculate for the Ag2CO3 is quite a bit smaller, 2 orders of magnitude smaller than the KSP for the silver chloride. So what we can compare when we're talking about like which is more soluble, we only can compare solubilities. We can't compare KSPs. If we're given KSPs for 2 salts and we're asked to determine which is more soluble, to be on the safe side, we have to go from KSP to solubility so that we can compare solubilities. We can't necessarily compare KSPs. In our next problems, we will go from KSP to solubility. We have the KSP for this silver chromate of 1.1 times 10 to the minus 12, and our problem is to calculate its solubility. So we look at the reaction as it decomposes. Notice we have 2 Ag plus CrO4 2 minus because of the fact that there are 2 silver ions for every 1 silver chromate. So we make our ice table. We have 2x for the change in the silver ion concentration, x for the change in the chromate ion concentration. And since they started at 0, those are our equilibrium quantities. We put it in our KSP expression, putting in the 1.1 times 10 to the minus 12. We solve for x, getting 6.5 times 10 to the minus 5. Now, x represents the solubility of the chromate ion, and the chromate ion is on a 1-to-1 molar ratio with silver chromate. So x describes the solubility of the silver chromate, which we see is 6.5 times 10 to the minus 5 moles per liter. Now we go to the next problem. We have KSP for lead iodide to be 1.4 times 10 to the minus 8, and we're after calculating the solubility of the lead iodide and the mass that would dissolve in 2.0 liters of solution. I would suggest that you stop this and you do that problem, and then you come back when you are done with that problem. Okay, so hopefully you did the problem correctly. You found x to be 1.5 times 10 to the minus 3, which is the solubility because lead 2 plus and the lead iodide are on a 1-to-1 mole ratio. To calculate the mass that would dissolve in 2 liters of solution, we take our 2.0 liters, we multiply by that solubility, liters cancel out, and we end up with the moles that will dissolve. We want the grams, so we calculate the molar mass of the lead iodide to be 461.0 grams per mole. That's our next conversion, and we get 1.4 grams of lead iodide will dissolve. So now, going on to the next topic, which is the common ion effect. So, we talked about the common ion effect back in chapter 15, chapter 15, and the presence of ions affect solubility in the case of these slightly soluble salts. We have that the solubility of silver chloride is 1.27 times 10 to the minus 5 molar or moles per liter. And we're after calculating the solubility of the silver chloride when we have 0.10 molar sodium chloride present. So we write out our solubility reaction. We put in our initial concentrations, 0 for silver ions, 0.10 for the chloride ions. The change is X for both. And we then have our values at equilibrium. We write out our equilibrium expression. We are dropping X with respect to 0.10, assuming X is very small. We can check that. Just makes the math a lot easier. And with that approximation, we get X to be 1.6 times 10 to the minus 9. We do our check, and it's way less than 5%. So the solubility is 1.6 times 10 to the minus 9 molar when we have the silver or the chloride ions present, and that is much less than the solubility when we have no initial chloride ions present. And that's, if you think about the Le Chatelier's principle, when we have something on the right side, it kind of pushes it to the left side. So the paragraph at the bottom, silver chloride is much less soluble when either silver ions or chloride ions are or is added. What if something were added that could remove the silver ions or the chloride ions? How would that affect solubility? Well, if something is removing those, then it would cause the reaction to go toward the right, and that would increase solubility. Well, if we add ammonia, like ammonia water, aqueous ammonia, NH3, then it turns out that that forms a complex ion with silver ions, and it then removes the silver ions from solution. That drives the reaction to the right and increases the solubility. Moving on to the next page. Which is on pH and solubility. So the presence of an acid or a base in the solution can affect solubility, much like the common ion effect that we just talked about affects solubility. It will affect solubility of hydroxide salts mostly. We will focus on hydroxide salts like this chromium 3 hydroxide. So we have that the KSP of chromium 3 hydroxide is 7 times 10 to the minus 31. We will calculate the solubility of it in pure water, in a buffered solution at a pH of 5.0, and then in a solution buffered at a pH of 9.0. So in pure water, we have a concentration of the hydroxide ions of 1.0 times 10 to the minus 7. That's a premise that we have been using since chapter 14. Pure water has the hydroxide ion concentration of 1.0 times 10 to the minus 7. Also, the hydronium ion concentration is that, but we're not thinking about hydronium ions now. So we write out our equilibrium expression, write the reaction that is, we fill in the ice table. Notice we have some of the hydroxide ions initially. We put our change in of X and 3X, and then our equilibrium values are what are on that last line. Notice for the hydroxide ions, it's 1.0 times 10 to the minus 7 plus 3x. Well, if x is very tiny, 3 times it is probably still very tiny, and that compared to 10 to the minus 7 is probably negligible. Okay, so we write out our equilibrium expression. We put in our value for KSP. We put in X for chromium ions. We put in the 1.0 times 10 to the minus 7 for the hydroxide ions. Notice we're cubing it, and we solve for X, and we get X to be 7 times 10 to the minus 10. We do our check, much less than 5%. Again, we're okay. So that means that the solubility is 7 times 10 to the minus 10. Okay, so going to the next one, the pH in a 5.0 molar buffer solution, or a pH of 5.0 buffer, we have the OH minus concentration to be determined from that pH of 5. Okay, so POH is going to be 14 minus the pH, so we have 14.00 minus 5.0, which is 9.0. And then from that, we determine the hydroxide ion concentration. You see that equation, OH minus concentration equals 10 to the minus POH, which equals 10 to the minus 9.0, which is 1 times 10 to the minus 9 molar. So we put that in as our initial concentration, and the chromium ion concentration can change, but not the hydroxide ion concentration because it's buffered. Alrighty, so we have the equilibrium concentrations in terms of X, and we have the other 1 times 10 to the minus 9. We write out our equilibrium expression. We're cubing the hydroxide ion concentration, of course. Putting in our numbers, putting in the X, we find X to be 7 times 10 to the minus 4. So that would be the solubility then, 7 times 10 to the minus 4 molar, and it's much higher than in pure water since the H plus present is removing OH minus, and it drives the equilibrium to the right. That is to say, if the pH is 5, then that buffer is primarily hydronium ions, not hydroxide ions. So there's a lot of that present that can interact with the OH minus, which is on the right side in our reaction, thereby removing some of it, helping to drive the reaction to the right, making the chromium 3 hydroxide more soluble. Now, I would say stop this and do the next problem. Do this one where we have the pH 9.0 buffer and we're running through the same problem. Start up again when you have completed that. Okay, so you have completed that one, and here is the solution. Our hydroxide ion concentration is 1 times 10 to the minus 5 molar. So we put those values in. Again, the change for the hydroxide ion is 0 since it's a buffered solution. And those are our equilibrium quantities. We write out our equilibrium expression, putting in everything. We solve for X and get 7 times 10 to the minus 16. It is now much lower than in pure water, and in our pH of 5.0 molar buffer because we already had a lot of hydroxide ion present, and that makes it so it's, according to Le Chatelier's principle, pushing the reaction to the left and not helping out with the solubility. Okay, now going on to our next section, which is on precipitation. So we have compared in the past Q with K to decide which way the reaction goes. Well, in this chapter, we are dealing with solubility. We are dealing with how much of the solid is going to break down to ions. So go to the reaction with lead nitrate and potassium iodide that's about halfway down this page. So PbNO3 2 aqueous plus 2Ki aqueous, forming PbI2 solid plus 2KNO3 aqueous. Now, imagine we have added a tiny bit of the lead nitrate and the potassium iodide. Well, if there's very small amounts, we may not get a solid, but as we add a little more of those reactants, eventually we will get a solid, that lead iodide solid. Now, to think about the lead iodide and how much we can add before we get a solid to form of these reactants, a solid of the lead iodide, imagine PbI2 solid in equilibrium with Pb2 plus aqueous plus 2I minus aqueous. Write out that solubility reaction. And what we do to decide if a precipitate forms on addition of reactants, we would think of that KSP reaction, and we would calculate a Q, and we would compare Q with KSP. So go back up toward the top where we have if Q is greater than KSP. So if that's the case, the ion concentrations are too high and a precipitate forms. So if Q is on the greater side of K from before, it drives the reaction toward the left. In our case, it makes for a solid. If Q happens to equal KSP, then the ion concentrations are right at their saturation point. They're as high as they can be, and a precipitate will not form, but if any more is added, a precipitate will form. If Q comes out to be less than KSP, so there aren't so many ions, then a precipitate will not form. The solution still could take more of a higher ion concentration. So our problem is, will a precipitate form when 1.0 liters of 0.040 molar lead nitrate and 1.0 liters of 0.20 molar Ki are mixed? We have the KSP for the lead iodide. The potassium nitrate does not form a solid. We do not consider that reaction. So what we do is we determine the concentration, the initial concentration of the lead ions and of the iodide ions. So for the lead ions, we take its liters, 1.0 liters, times its initial molarity, this stock molarity, and then we divide by the total volume, which is 2.0 liters, and we get 0.020 molar. For the iodide initial concentration, we take its volume, 1.0 liters, times its molarity, 0.20 moles per liter, divided by the total volume after we mix those two, 2.0 liters. We get 0.10 molar. Basically, we are diluting each solution by a factor of 2. Those are our initial concentrations. So Q is Pb2 plus initial times I2 minus initial squared. So we have 0.020 times 0.10 squared. We get Q to be 2 times 10 to the minus 4. That is substantially greater than KSP, and since Q is greater than KSP, a precipitate will form. Our last section is on qualitative analysis, and in this area we will get into flowcharts. You will be doing a little bit of lab work using this technique. It's a technique where we are not after numbers of compounds present, we are after what compounds are present. So let's say that we have a mixture of silver ions, lead ions, and barium ions. So we have Ag+, Pb2+, and Ba2+. Now, how we would use this in practice is we in the lab will get an unknown, and that unknown could be composed of all three of these ions, one of the ions, or two of the ions. And our job would be to figure out which ions are present. Alrighty, so here is the information on how these react with various substances that we will use to do the analysis. So in the lab, we would actually be doing these reactions to get our results, but we would have to know what to expect. Okay, so here we go with how they react, what to expect. So silver and lead are insoluble in a chloride solution. Barium is soluble in the chloride solution. So when we add sodium chloride, for example, to our mixture, we get a precipitate to form with the silver ions, and that's reaction 1, and with the lead ions, and that's reaction 2. Now, we would centrifuge the solid so it's very much in the bottom of the test tube, and we would then pour off the solution at the top. The solution at the top, since in our situation here, our pretend situation, contains barium, the solution at the top would have the barium ions, and the precipitate at the bottom would contain the silver as well as the lead ions, both of them as chlorides. So what we would do is test the liquid solution, and we could do that by adding, for example, sodium sulfate to it, because barium 2+ and sodium sulfate 2- form a solid, this barium sulfate solid, and that's reaction number 3. So that would tell us, yep, that's that barium in the top, in the liquid part. And then we have to now work with the precipitate. Well, it turns out that lead chloride solid is soluble when hot. So, and the silver chloride is not. So what we would do is take our test tube that contains the silver and the lead chlorides, and we would stick that in a beaker of hot water. The lead chloride would dissolve according to reaction 4, and we would separate the solid, which is the silver chloride, from the liquid solution, which contains the Pb2+, and then to test for sure that the Pb2+ is in the liquid part, we would add iodide, like sodium iodide, to it, because the lead forms a yellow solid as given by reaction number 5. Now, the solid in the test tube is silver, but a way we could test that is to add some ammonia to it. It forms that silver ammonia complex ion that we talked about before. That causes, and notice that that's an ion, and so that causes the silver chloride to dissolve. And then if we wanted to even go on further, we could add some source of acid, some source of H+, because the H+, being an acid, likes the NH3 of the complex ion being a base, and we get then silver ions back. Now remember that according to reaction 6, we have chloride sitting in that test tube. So the silver ions and the chloride ions would cause a solid to form. The overall reaction for adding the ammonia is given in reaction 7. So that would indicate that we have the silver ions for sure. Okay, so those are how this will react. Now we can summarize those in a flowchart, and that helps us to see the overall reaction better. So the way we do a flowchart is as I've shown here. We have our ions. Now remember that these are ions that could be present in the unknown solution. We could have silver, we could have lead, 2+, we could have barium, we could have 2 of those, we could have all 3 of those. So how we would go about testing it. First thing, we would add the source of Cl-. In this case, it's 6 molar HCl. So the Cl- is the important part there. The silver and the lead, whatever's present of those two, will form a white precipitate. Notice we write that. We put the precipitates on the left side, and so we have the silver chloride, we have the lead chloride on the left. Those are what form solid-wise, but the barium doesn't, so it's still, the solution contains Ba2+. And then, following along with the barium 2+, we would add the sodium sulfate. That would be a source of sulfate. We get a white solid. That indicates barium 2+ is present. Going back to the solid, we heat it, so that's that hot water, and we get the silver chloride to remain as a solid, but the lead part of it will dissolve. Now, to test for sure that we have lead present, we add a source of iodide. It is sodium iodide, and we get that yellow solid. That indicates Pb2+. Okay, so going back to the white solid, the silver chloride solid, we would add ammonia to it, and then the solution now contains the silver ammonia complex, as shown there. We would add a source of acid. We're after the H+, and here we're given to add it as nitric acid, and we get a white solid if we have silver present. Go back to those reactions number 6 and 7 from the previous page. That indicates silver ions. So that would be our flow chart for this, this scheme. You will be doing a lab work from 2 qualitative analyses, and you will think about the information given to you as to how they react, how you would write a flowchart from that, and so forth. Okay, so that's coming in the lab. We are done with chapter 16 now. So do homework problems from the textbook. You have a quiz on chapter 16. Check when it's open. Make sure that you get it done in that time period. And you have an exercise to do, and make sure that you do that and get that turned in by the time it's due.